let's get moving. All right, welcome back. We are Game 2005 in the fall 2021 semester at George Brown, and it's week 12, part 1 of our broadcast for game physics. Let's take a look at where we're sitting. We're sitting right now on the week of November 25th. This is November 25th today, and we're talking about 3D collision detection. We've already kind of done 2D collision detection. For the most part, you and Joss have kind of gone over that already. I'm going to go into more of some hints and tips on how to do that. This week, we're going to release assignment 4. We're just working out the final details of what that is, so that hasn't been officially released up on Blackboard yet with all the details. There might be a stub that's out there right now, but that's it. And assignment 3 is also due by the end of the week, right? So I know people have been asking for extensions. It's really difficult at this stage in the game at the end to provide an extension because we can't push back anything beyond what we already have. So the answer is going to be probably no, unless there's some kind of medical thing or something that you have that's urgent, that requires you to have an extension. Yeah, you're going to do the best you can. It's due on Sunday, I believe, and we can check that out on Blackboard. Let's go on Blackboard and check it out. So if you look at assignments, right, we have assignment 3, part 1. That's the first part. And that is due Friday, November 26th. What I can do, I can move this to Sunday. That's the best I can do. Right, so I'll say it's updated. So say updated. Say that it's going to be due Sunday, November 28th. That's what I thought. 28th, 24th. That's the best I can do. I can't do anything more than that. And the reason for this is just because of just the vast amount of stuff. I'm already behind with you guys. And the more, this is the crazy stuff, the more I give you an extension, actually, the more behind I become, which is kind of the way it works for me. So, it is what it is. I'm hoping that you guys can get through it and it's not totally terrible, but we'll just put in here that it's been updated from me, and hopefully you guys have a chance to be able to do that. So A3 part 2 is going to be due on, that's going to be due on the last, on the week number, let's go back here. It's supposed to be the week of December 9th. So that would be probably, instead of December 9th, it'll probably be December 10th. Friday probably is when it's supposed to be due. But why is that? Now that, guys, don't ask for, as we move towards the last week, there's no way that we can extend you beyond what it's going to be. And the reason why I'm telling you this is because the final test, if we make this practical, Joss and I, those two things will overlap and it'll be a very terrible experience for you all. And that's nothing that we want to do. So please just put that in mind, that that's what's coming forward. That's what's happening. Okay. All right. So without further ado, instead of, the assignments and everything else, let's do this is 3D collision detection today. And it's something that you've been doing already with Joss in Unity. And we've given you some tools and a starter to get you going. So that should help you. So again, when it comes down to it, there's a bunch of different techniques that we've talked about as a review. We've used geometry, linear algebra, some knowledge about trig, calculus, a lot of that kind of stuff we can use for collision detection and for physics in general. All right. So this section covers some more fundamental geometric types, including things like line segments, planes, and boxes. Right, so kind of a review of some of the things we've already talked about, and in addition, some more algorithms, kind of related to 3D collision detection. Okay, so that's one thing. Where this is what this A3 part 1 is kind of all about in many ways, right? So really, when we think about it, when we start with a basic shape, a line segment, we can see it as a struct, right, where it has a vector 3 start and an end. Notice we're using vector 3s because we're talking about 3D collision detection and response. The line segment is probably the most fundamental thing that we want to talk about in 3D. Once we start thinking about a line segment, well, before, between lines and vectors, again, remember maybe when we first started off way back in the day, I said that, you know what, I want to show you guys Blender. I may have done this kind of a Blender demo with you where I kind of said, hey, here is Blender. And, I asked you guys maybe, what are the fundamental building blocks of every geometric shape that you can possibly have in Blender? And we said that the fundamental blocks are vertices, edges, and faces. Those three things, right? So verts would just be a vector 3 in three-dimensional space, right? So again, you can modify this vertex so it kind of goes anywhere you want, or a point. Then you have an edge, right, which is really this line segment that we talked about before, which is what we're saying right now, an edge. And finally, we have a face, right, which is a plane. That's what it is, a plane that has a normal. All right, so that's what all fundamental shapes in, or primitives, we like to call them, in 3 dimensions, use these properties. Okay, so that's something that we have to think about. So what we're talking about here is an edge, right? Once we have an edge, which is a line segment, there's a lot of really great things that you can do with it once you understand what this is, what a line segment means in 3D. Okay, so again, to calculate any arbitrary point on a line, right, as an example, Sherman, you're saying aren't planes made from 2 triangles? Yes, yes. But when we think about planes themselves, as an example, any kind of plane, whether it's a triangular plane or whatever, it is a bunch of points, right? If you want to think about it, an infinite amount of points, that are, kind of in an area that you've defined with a top left and bottom right kind of coordinate frame, right? So yeah, so it could be a quad as well, for sure. So, and we want to use quads as much as possible, like Neil is saying, for any kind of organic modeling. If I'm going to use organic models, like let's say I create stuff where I have a 3D model that's running around, I'm definitely going to want to use quads and not triangles, because triangles are, they deform a lot worse than quads. But however, Neil, going back to when we actually extrapolate and create a mesh, we want to triangulate the quad at the end anyway, because otherwise, your graphics engine won't know how to generate it. And you can actually create your own meshes programmatically in Unity. I recommend, if you're interested in that practice, try it out. I think it's very interesting. And you can start off with the number of triangles that you have. And building a mesh programmatically is pretty awesome. It kind of gives you a lot of really cool things that you can do in Unity from a drawing perspective. Okay, so when I want to calculate any arbitrary point on a line segment or edge, you can use the following parametric equation, where the start and end are the start and end points, vectors, and t is the parameter. And if we think about what this is, the t factor, this is kind of, we're using linear interpolation to kind of say that I want to take the start plus the end minus start multiplied by t. The t point would be a number between 0 and 1, right? Where 0 is 0% and 1 is 100%. Okay, that's kind of linear interpolation. So for convenience, what we can do is we can add a member function to line segment that returns a point on the line segment given a t value. So example, I'm going to get, I want to return a vector 3, right? So that's the point that it returns, right? And I'm going to pass in a float t, and t would be the t value, or the point on the line that you're looking for, the percentage from one line to the other, right, as an example. And I say, okay, on this line segment, given the start of the line and the end of the line, if I give you this t value, I'm going to return a vector that's on that line, a vector 3 that's on the line itself. So if we think about this, line segments, and here's another really cool thing that we can use in 3D, line segments are kind of like the building blocks of a lot of stuff. Things like AI, from a line of sight detection, that kind of stuff. We can make them, we can use rays for ray casting and all that kind of stuff. I want to detect ground. A lot of times I use ray casting to detect the ground in a 3D platformer or even a 2D platformer, right? Because what I can do is I can say, well, if I kind of shoot a ray down and if it intersects with something else, some kind of collision detection, then I'm grounded. And if I'm not intersecting with anything, then I'm in the air, whether I'm jumping or falling, right? That kind of thing. So line segments are a great way of doing that, and we usually call them rays. Okay. So again, for example, firing a bullet in a straight line and testing for landing on the ground, like we said, aiming reticles at or sound occlusion tests, anything like that. And sound occlusion tests are awesome because if you think about this, if I fire a ray from the sound generator, let's say, for example, I have something that's making a sound and it's inside of a three-dimensional object like a kitchen or something else like that, right? And you want to hear muffling, sound muffling, that kind of idea in another part of the house, right? Well, then what you can do is you can make that sound bounce off different surfaces to create realistic sound effects or spatial sound, right? And we use ray casting for that, which is kind of really cool. So another useful operation is finding the minimal distance between a line segment and an arbitrary point. Okay, so I have some kind of point and I want to find the minimal distance, right? And imagine that a line segment starts at point A and goes to point B, right? Given an arbitrary point C, let's say here, you want to find that the minimal distance between the segment and point C, there are 3 different cases to consider. You guys have seen this with working with JOS, 3 different cases, right? And we actually talked about this last week in a little bit as well when it came to collision response in 2D, projection, okay? Notice that there's a distance between the outer edge of the left edge of the line segment and a point C, and there is kind of a distance between the outer edge of, the line segment near point B, right? And those are 2 different cases. So where actually C is away from the line. Okay, then there's the other point, and this is the point that really matters to us. Okay, the point where there's a point C that is, we can project point C onto the line segment AB. And there's this displacement from A to B, right? If you will, right? From A to B, there's some kind of vector P, as an example. And that is what we want to find. What's the closest point from this point C to line segment AB if point C is within this area? Okay, so again, C in this case is outside of this area, outside of the line segment. It's not going to fall down, right? So it's closer to B. This one is closer to A. And by the way, you can also reflect this in the other direction, right? I'm just going to annotate that so you can see it. So let's just draw those lines out there. So again, I can make it so that it's actually in this direction. So I can kind of mirror it this way, right? And the same thing goes with if there's a line here. But what we're doing here, which is very interesting, is again, we are casting shadow. So this shadow, this line where it's inside, it's kind of the distance between A and B, it's within, right? We care about this very much because if it's within this line segment, as an example, then it's going to either hit an edge or the surface of a plane. Okay, that's the same kind of calculations we're going to use. So something that it's not like we haven't used, this kind of stuff before, right? Or we haven't talked or discussed about something like this. So in the first case, we called in figure A, the angle between A and B and AC is greater than 90 degrees. And you can test this by using dot product. We've seen that before, right? Because a negative dot product between 2 vectors means that they form an obtuse angle. And if this is true, the minimal distance between C and the line segment is the length of the vector AC. In the second case, shown in figure B, this one, right? The angle between BA and BC is greater than 90 degrees also. So both of them are greater than 90 degrees. As in the first case, you can test this with dot product, and if this is true, the minimal distance is the length BC, right? AC, BC, that's the distance. So if it's on the other side, we can say that it's greater than 90, or you can use dot product for positive and negative results, right? And depending on what you get, you can just kind of decide with that result what the condition is. And the final case shown in figure C, you draw a new line segment from AB to AC, and that's perpendicular to AB. The distance of this new line segment is the minimal distance between C and AB. And to figure out this line segment, you need to compute the vector P. And you already know the direction of the vector P, as it's in the same direction as the normalized AB, right? So again, if I was to go up here, the normal between A and B is like a little tiny line. Remember how we've done this before, but I'm just reminding you of this kind of stuff because I know some people have forgotten. Imagine we have a line of unit length 1, right? And that's kind of hard to see. Maybe I can use a different color. Instead of red, we'll use a green color. Yeah, we'll draw it again. So let's say we have a unit length of 1. Let's suppose that this is unit length 1, right? Let's suppose that draws a line from A to B. It's not the whole length of the line, but it's a length of 1. So 1 unit. That is a normalized, and the magnitude has to be that way. So if I was going to draw from A to C, the normal from A to C also would be 1 unit in length, something that looks like this. Okay, so you wouldn't want to, something like this way, right? So that's the normal. It's a normalized, value, unit length 1, right? And unit length 1 means the total distance from A to whatever that normal is will be a distance of 1 magnitude-wise. Okay, so that's what it is. And so it kind of says that. It says that to do this, it says we already know the direction because it's the same direction as AB. We know that. We can just take a line segment, start, end. That's the direction. And to figure out the distance of P, you apply a property of the dot product called scalar projection, which is something you've been doing over the last few weeks. And given a unit vector and a non-unit vector, we want to extend or contract the unit vector such that a right angle forms from the non-unit vector, and the dot product then returns the length of this extended unit vector. Okay, that's what it does. So here are some code. Here's some code, a little bit of code for you to help you out. So here's minimum distance. Now, if you don't have this already in C#, this is I want you to consider this as C++ or something like that. Looks like C++ to me. And obviously, you're going to have to convert something like this to Unity to help you out. So again, if you think about it, if I have a line segment, or in your case, a plane that you've defined, we want to find the minimum squared distance. Notice the minimum squared distance is far better per frame than the actual distance. If I use vector3.distance or vector2.distance to determine a distance, I'm actually using square root. We don't want to use square root. We've talked about that as bad, computationally expensive, right? So we want to pass in a vector3 object, which we consider a point, right? And then from that vector3 point, what we say is AB is the start, the end of the vector, the end of the line, minus the start of the line. So this is inside the line segment algorithm itself, right? And then we can use this to calculate AB, BA, AC, and BC. We calculate all these things ahead of time. And then we have the 3 cases. Case 1, okay, is this true? When I take the dot product of AB and AC, if that dot product is less than 0.0f, right, so less than 0, so a negative number, we know that we want to return the length, the squared length of AC. AC, we want to find this is the minimum distance, okay? Otherwise, case 2, if the dot product BA and BC, right, notice that it's a different thing, BA and BC. If that is less than 0, again, then we want to return the squared length of BC. BC, this one, okay? And then case 3, if everything goes well, if C projects onto the line, then we say that that is the other condition. So these are the 2 conditions. Otherwise, if it's not one of these, then it must be this one, right? We don't test for if it's within. We know if it's within when it's like this. And we say that let's compute P first. So P would be the distance from A to the projection of C onto AB. That's what it is. And we take the dot product of AC and AB. And once we have that, that is a scalar value. And what we want to do then is we want to say that P, right, is take that scalar value and multiply it by AB, where AB again is the distance, the difference between the end and the start, the line segment itself, the whole distance. Okay, and then once we have that, then what we want to do is we want to return the squared length of AC minus P, right? And then we want to get that squared length, and that is the minimum squared distance, as an example, because it returns a float from an arbitrary point C onto a line segment. Once we have that, guys, this is building blocks we're talking about, right? Once we have this kind of stuff, we can do better. We can build on this kind of stuff, right? So this is your code. So if you've been struggling with finding solutions to some of this stuff, I know Joss has been giving you some of it. The stuff I'm going to be sharing with you today is going to help you with assignment 3 part 1, hopefully. Okay, so we know about lines. We've talked about lines at a great degree. Let's talk about planes. Again, a plane is a flat two-dimensional surface that extends infinitely, right? Much as a line is a one-dimensional object that extends infinitely. In a game, you can use a plane as an abstraction for ground or walls. We've done that before. And the equation of a plane is as follows. P times N, right, the normal, if you will, plus D, which is equal to 0, right? So again, P is an arbitrary point on the plane, any point on the plane. N is the normal to the plane. And D is the signed minimal distance between the plane and the origin. Okay, the plane and the origin of the world, which is 0, 0. Okay? So that is the equation for that line. I'm okay if you get it to work anyway. Neil's asking, do I have to use algorithms like this? You don't have to. I'm giving you some points for those people who are struggling, who are having difficulty understanding things. So that way you see some of the algorithms that I'm giving you here. In code, a typical test is whether a point lies on the plane. This is what we've been talking about with you guys so far this semester, and thus satisfies the plane equation. Because of this, the definition of the plane struct only stores the normal and D. So all we get is a vector 3 normal, right? Remember, the vector 3 normal is a normalized value, length 1. That's what the normalized value should be in a specific direction. It gives us the direction, and it's perpendicular to the plane. So at 90-degree angles too. That's what we're talking about. And some kind of float, which is the distance from the origin. That's what D is. Distance from the origin for the plane. Okay. So by definition, then, a triangle lies on a single plane. So given a triangle, you can derive the equation of that plane. You can compute the normal to the triangle with the cross product. So that's another thing. You guys have covered cross product with Joss, yes? Or no? Cross product is different than dot product. It produces different things. Again, which corresponds to the normal of the plane. So if I want to find the normal of the plane, I can use the cross product. That's what it does, okay? And we already know an arbitrary point on the plane, right, as well, because all 3 of the vertices of the triangle are on the plane. We know that. So we have 3 arbitrary points that are sitting on the plane, right? Given this normal and point, you can then solve for D as in this following listing. So example, I have a vector 3A, B, and C. Those are the 3 points of the triangle on a plane, okay? So 3 points of a triangle. And then what we can do is we can compute vectors from A to B, from A to C, as an example. And what we want to do is we want to get the cross product and normalize to get the normal. So that's what this is, the plane constructor, if you think about it, right? When I construct a plane, what it's actually saying is give me 3 points on the plane, 3 points similar on the plane. And then I can tell you what the normal is. I can normalize the normal value where I get a vector 3 cross product. This is the direction, right? And then I want to take that direction vector, right, and then normalize it. Once I've done that, I've got the normal, okay? And then for the distance to the origin, I do the dot product, okay? And there you go. So D is equal to the minus P dot N, which is what's giving you this, this distance. So now that we have this, we have the distance and the normal. That's going to give us a great help to do that. And in Unity, I'm just going to pull this up here to help you again. If you go to Unity, and if I go to Vector 3, Vector 3 has a pile of functions that you can use, right, to help you out. All right, so it has normalized, it has square magnitude, and so on. It has a bunch of things that you can use. It has distance. So distance is the actual distance, not the square distance. It has dot. It has lerp, right? As an example, min, max, normalize, project, right? Projects a vector onto another vector, right? It has these things already for you that are set up, signed angle, and so on, right? So it has all those things. Okay. So, this is fantastic in terms of trying to, find out, how things work. And it also says this, makes vectors normalized and orthogonal to each other. This is kind of neat. There's a lot of stuff here that you can use to get information about how things would work. Remember also that MathF, there's also a MathF library that you can use as well. So not just the Vector 3 library, but we can use Unity's MathF library. So if I go to Unity MathF, right, and if I was to search that up, here's the MathF library for Unity. It has a bunch of functions that you can use to help you out. Okay, tons and tons of them, right? And a lot of these functions, guys, I have to admit that I've stolen and I've brought into SDL engine that you guys were using earlier. Yeah, that's fine. Up function, no problem. So anything like that is good. So you can see that there's a ton of functionality here that you can use, kind of anytime you want, right? So this is kind of the way it will help you. A lot of these functions, whether it's in the math library or in the Vector 3 library, will help you to calculate normals and to do all that kind of stuff. Okay. So hopefully that helps kind of orient you a little bit, right? And the stuff that we're talking about. What is it that's... All right. So that's pretty cool. So that's what it does. It computes the normal. Bounding volumes. Let's talk about that. So modern 3D games, they have characters and objects drawn with thousands of triangles, right? And we're determining whether two objects collide, it's not efficient to test all the triangles comprising of the entire object. Imagine that. And for this reason, games use simplified bounding volumes such as boxes and spheres. And you've been seeing that all semester so far. We've been talking about bounding boxes right at the beginning when you got it back from break in week 9. That's what Josh has been talking to you guys about. And when deciding whether two objects intersect, games use simplified collision for calculation, and this yields greatly improved efficiency. Okay. However, there's issues, and we'll talk about the issues with this. We talked about them actually earlier last week with how when we do collision response for 2D, similar in 3D, right? So we have a struct sphere in this particular case. Again, this is all review for you. We have a vector 3 that is the center, and we have some kind of float that is the radius. This defines a sphere itself, right? And once we have that, bounding spheres fit around some objects better than others. For example, a sphere around a humanoid character has a lot of empty space between the character and the bounds of the sphere, and having loose bounds for an object increases the number of false positive collisions. We've talked about this. False positives are bad, meaning the bounding volumes for two objects intersect, but the objects themselves do not. And for instance, if a first-person shooter used bounding spheres for humanoids, players could shoot away to the left or to the right of the character, and the game would count that as a hit, which we don't want. But however, the advantage of using bounding spheres is that the intersection calculations are extremely efficient and super easy to calculate. And that's why your first game, the one you're making for assignment 3 part 1, is all around sphere collision detection, really. Sphere and planes or sphere and sphere. Those are the two things we've asked you to do. Furthermore, rotation has no effect on a sphere, so a bounding sphere works regardless of the rotation of the underlying 3D object. And for some objects like balls, spheres perfectly express the bounds. All right, so that's kind of an important thing as well. Now, obviously, this is inefficient. You're going to have a visual collision a lot of times in a weird way. and the box will behave a lot differently. If it's a box, some kind of cube, or a rectangular prism, as an example, and it's inside of a sphere, or some kind of humanoid character, I would say that in those two conditions, right, definitely you can do this, but this is a no. I wouldn't do this. This is okay, because this is kind of spherical. You have a little bit of space here, as well as here, but that's going to be hard to detect in a three-dimensional environment. This will be easy to detect because you have all this space right here and all this space right here, right? That's a problem, right? And crates, boxes, and rectangular prisms also bad because when they sit down on themselves, if you kind of stack something like crates, yeah, it's not going to work, right? So obviously, some kind of cubic volume or a bounding box instead of a bounding sphere is better for those kind of environments. And again, this is all review. You guys should know all this stuff. Nothing that's challenging you in terms of the way things are going. In 2D, we have an axis-aligned bounding box, or AAVB, we talked about, and it's a rectangle where the edges are parallel to either the x-axis or the y-axis. Similarly, we can do the same thing with AAVBs in a rectangular prism, where every face of the prism is parallel to one of the coordinate axis planes, either the x, y, or z plane. And we can define an AAVB by 2 points, the minimum point and the maximum point. Sometimes we also call this the extents. So if I was going to, say them, we can say AKA, also known as the extents of a bounding box. That's what it is. That's what the minimum point and the maximum point are. Minimum point and maximum point are the kind of the minimum vector and the maximum vector, the extents. In 2D, the minimum point corresponds to the bottom left point, while the maximum corresponds to the top right. But here in 3D, you're going to have a min and max somewhere outside of, they're not probably on the same plane. Okay, typically. If they were on the same plane, you would have a two-dimensional item. Okay, so if the min and max were on the same plane, right, 2 points in the same plane, then you'd be defining a plane, not a bounding area, a bounding box. Okay, so this letting you know that. So again, it carries over into 3D where we have the struct for an AAVB has a minimum and maximum value. And a useful operation with an AAVB is constructing it from a series of points. For example, when loading in a model, you have a sequence of vertices. You've done this probably in OpenGL, and you can use the sequence of vertices to define an AAVB for the model if you really wanted to, right? And to do this, you can create a new function called update min max for the AAVB that takes in a point and updates min and max accounting for this point. So again, you can have a min, the minimum value, between min x and the point x, the new point that you're bringing in, right? So if I have the minimum point, remember the minimum point has an x, y, and z value, right? So I'm using the min function, also exists in Unity, by the way, the min function. I'm getting the minimum between one floating point number and another one, right? And I want to know which one is minimum, right? Depending on which point is minimum from this point, x, y, and z, I'm doing a member-wise comparison between the point and the minimum vector, right? And depending on which one is minimum, I'm going to update the minimum point. And I can do that for every point that's in my model, okay? Then I can find the extents. If I analyze a model and I go through all the vertices, think about this as all the vertices of the model, I can find the extents of the model this way. So I can exactly kind of create the bounding area that I need for a model, right, based on the minimum and maximum points. Okay. Now, again, this is assuming that the model is not spherical. You can still do it with sphere, but then you're going to have that area, just like if you're trying to put an AAVB around a sphere, there's some other problems with that. It's better to use a spherical bounding area for a spherical shape, and some kind of rectangular prism, AAVB, for a rectangular kind of shape that you're going to bound. All right, that's just normal common sense, but I'm sharing it with you again as if you don't know anything, so please forgive me. Again, because we don't know where the new point is in relation to all the other points, you must test every component independently to decide which components of min and max should update. So you can kind of say, now we have the minimum and maximum vector. And this is very, very important. We can construct a min max for an AAVB. And then once I have that information, the minimum and maximum points, once I get this, then I can start thinking about how to do overlaps. Okay. So again, axis aligned bounding boxes, we give a container of points. You first initialize min and max of the AAVB to the first point of the container. For each remaining point, you simply call the update min max, right? So again, a container of points is an array of points, right? We do an update for every point for every vector or vertex, if you will, inside of the object. We run this for loop for every single vertex where we update the min max based on the point that you're passing in. Okay, that's what you're doing. And then you can get something that looks like this. By the way, this would have been awesome if we did it in physics, right? Imagine in AI, when we were doing AI in the beginning last year, right? For some of you, it would have been 2 semesters ago for some of you, and some of you last semester, right? That's more like it. Then we could have used this same idea. If I want to rotate an object, right, in 2D, then I can run the same idea of updating min and max. Instead of using X and Y and Z, we could just have used X and Y. When I rotate, I update the bounding area, the bounding box, based on the rotation of the object. So very, very simple to do. Okay, we want always to get the extents, and then an area like this, if I rotate an object, is pretty good, right? Now again, this is pretty good for a human, kind of an organic character. This is pretty good. This, not so good, right? Would you agree? Because we have all this in here and all this in here, and that is a lot of noise, right? It's a lot of, really what we want to have is something that looks like this, but that's not an AAVB, is it? If we do something like this. That's not axis aligned. This is axis aligned. So is this, right? This is not. And remember, axis aligned calculations are way easier than non-axis aligned calculations, like using something like separating axis theorem by using the hyperplane and so on. Okay, so that is something we have to consider. All right, again, one way to compute an AAVB after rotation is to first construct the 8 points representing the corners of the AAVB, and these points are simply all the possible permutations of min and max, x, y, and z components, and then you rotate each point individually and use the update min max functions to create the new AAVB from these rotated points. Okay, so what do we mean by this is, here is the rotate function. So if I want to rotate an AAVB, I can pass in a quaternion, right? Again, this is suggesting that we know what a quaternion is. In Unity, you have quaternion rotations, or you can use Euler rotations. We haven't talked about rotations so far. I don't think that, I'm not sure that Joss talked about that with you, because they're all spherical things that we're talking about so far. And you haven't really worked out, if I'm not wrong, I don't think he's talked about AAVB type collision detection, just not yet. Am I right? Yeah, so if you think about this, right, passing in if I'm rotating a point, if I'm rotating an object in 3D, when I pass in this quaternion Q, right? Remember, a quaternion, it has a some imaginary data, right, for a quaternion. If you remember quaternions from linear algebra, right, maybe you did that, maybe you didn't. But what we want to do is we might have a transform function. Again, this is all pseudocode, right? We have a minimum point. It's always the corner, the first minimum, right? And then we want to say it's permutations with 2 min and 1 max, right? So we take that Q and I want to rotate it. Q would be the quaternion angle that we're moving. We're kind of taking that quaternion matrix and adjusting it or rotating it across. So it's like a 4x4 matrix equivalent. And we're rotating the object using a 4x4 matrix. Okay. And again, then once we get those new points, we get the new min and max, And what we do is we update the min and max for all the points that have all been rotated. Every single point on the object has been rotated, right? Kind of has a transform or a translation, right? Using this transform method, right? So again, rotate first point, right? Now, one thing to note is in Unity, right? And again, I'm not sure if Joss will allow it, and I gotta talk to him about it. But if we talk about in Unity, let's go back to that vector 3. So vector 3 in Unity. Let's go back to that API for a second. So take a look at what a vector 3 gives you, right? It gives you angle, distance, and move towards. That's kind of part of that, and then rotate towards. So you want to rotate a vector towards a target. That's going to help us if we do any kind of rotations in Unity. It allows you to change a vector being a point. And remember, when I rotate, all I'm doing is I'm changing the orientation of the up or forward vector, right? As an example, the up or forward number towards where I'm rotating towards. So that means that the normal itself changes direction. That's what I'm doing when I rotate towards. And you can see that we have a bunch of static properties that we can always call forth with a vector. For example, one of them is forward, which is the 0, 0, 0 point. But this forward has to be relative to what you're pointing to. Forward can be updated. By default, these values here we use and multiply to create, especially things like back, right, up, and so on. Those are default values that we can use to do our calculations. All right, and if we look at quaternion, quaternion is also available to us in Unity. We have X, Y, and Z rotation components as well as the W, right? And W is this imaginary component that we use. We can also convert we can use the Unity, a quaternion to use Euler angles. So quaternion Euler, right, is a way of translating X, Y, and Z, right? So here's an example where I can say that I have a quaternion, current rotation, as an example. And then what I can do with it is I can use Euler angles, right, to change, to make a change to the game object, right? So one thing that we know is that the transform always has, there's three properties in a Unity, in the Unity's transform, right? It has a rotation, a position, and a scale. Those three things: position, rotation, and scale. Just like we do in Blender, location, rotation, and scale. It's kind of the same idea, right? And so we can use the transform rotation value, which is just a vector 3, if you think about it. And we can rotate it using Euler angles as opposed to using quaternion. Okay, so that's kind of something we can do. And you can see that there are some examples on how to, to do things down here. Okay. So that's something that we have access to. And again, what Euler? No, it's Euler typically is what I've heard it, right? Euler angles, yeah. When I looked at it, I said the same thing. I was like, Euler, like Bueller, right? And people made fun of me when I was learning about it. They're like, no, it's Euler. I'm like, okay. Right, so that's your rotate function. So what about this oriented bounding box? We have a axis aligned bounding box, but this is optimal, right? This is what we want when it comes to to rotations, right? The proper box rotations. I want to rotate it without doing those fancy rotations like this. And now we can see that the OBB has three different pieces of information, right? We have a center point, a quaternion for the rotation, and the extents, width, height, and depth. That's what extents are. So we have a vector 3 that gives us that value, X, Y, and Z, width, height, and depth. That's what they end up being. Okay, so those two vectors, two vector 3s, and a quaternion rotation, right? So give us the angle that we're currently at, if you will. And again, it's tempting to use OBBs, but the downside is that collision computations are far more expensive with OBBs than with AAVBs, right? AAVBs. So OBBs, again, this oriented bounding box, okay? The other one is a capsule, okay? So capsules are great. Capsules are actually things that we know, right? If you think about this, right? We have a capsule really is a line segment with a radius. That's what it is, right? So we can sit there that we have a line segment. If we plan to draw this out, what is a capsule, right? Well, we can draw a line segment from here, right? I love when this happens. Let's draw another color. How about that? We want to draw a line segment from here to here, right? That's the line segment of my poor drawing ability, right? So if you look at this line segment, really, if it's like a line segment between two centers, right? I have two spheres. I have a sphere on the top, and I have a sphere in the bottom, separated by this line segment. That's really what we're doing. Here's the line segment, right? And this is almost like you can form a capsule by using a cylinder as well, and a cylinder and two spheres, one on the bottom, one on the top. See, I wasn't wrong, Neil. Euler. They got mad at me when I said it. I told you, right? So I use Euler from now on. So then we have a line segment and a radius. And then capsules are really popular for characters because they align nicely. We don't have a lot of visual collisions that are bad. I mean, look at this. There's a little bit here, but who cares? And there's a little bit here and here, but not very, very bad. It's pretty good. A lot of what we use capsules for with three-dimensional characters because there's not a lot of waste. And the other reason why we want to use capsules is because if I was to collide with a plane, let's suppose I want to calculate, and if I had a plane that kind of went to like here, let's say the character was standing on a plane, like so, then I can clearly see that the sphere is overlapping or touching, whether it's a bounding box or whether it's a plane. I can do a sphere, plane, or sphere box collision detection very easy. And so it's low computational expense, if you will, compared to using some kind of oriented bounding box, right? Oriented bounding box, super expensive, way more difficult to do, and it's complex. All right, so capsule can also represent a sphere moving over a set period, like a swept sphere that we'll talk about later on. And I think Joss has shared a PowerPoint with you guys relating to that. Oriented capsule, not really required, right? Because we just need the top and the bottom. And once we have the centers of the capsule, we have rotation, don't we? Right? So that's kind of interesting the way it works, right? So think about there's a vector here and there's a vector here, and it's a line segment in three-dimensional space. So I can put that line segment in any direction, right? And now I can use capsule, kind of use the capsule as a bounding area. So again, so if we think about a capsule also as a swept sphere, so a sphere that goes from here at one point in time all the way to here, that's another way to think about it. Moving radius. And sometimes what we want to use, a game may need bounds for an object that are more accurate than any of the basic shapes. For a 2D game, the object might have bounds representing as a convex polygon, okay? And recall that a polygon is convex, right, if all of its interior angles are less than 180 degrees, right? Concave is evil. We don't want to, concave objects, we want to surround with a sphere or a box as much as possible, right? Because it's very difficult for you to do concave calculations. All right, there's some issues with that. Okay, and some of the especially SAT doesn't work great at all with concave calculations. Right, so convex is easy. What we have is a with a clockwise ordering. Remember convex polygon? We have an array as an example, or a vector in this case. A vector is like a managed array, like we talked about in C++, of vector 2 vertices in a clockwise winding order, right? We've talked about that winding order. So again, if I was going to draw points, as an example, let's draw some points. So this is point 1, clockwise winding order is exactly in what I'm drawing, right? So this is 0.3 and this is 0.4. So this is 1 clockwise winding order, right? With my poor drawing with the mouse capability. 1, 2, 3, 4 clockwise winding order. All right, that's what it means. And it doesn't matter how many polygons you have, how many points you have, you can create any polygon that, as long as it's convex, with this kind of situation. All right, this kind of expression. All right, cool. So again, these vertices should have a set ordering, and without an ordering, intersections are more difficult to compute. So Shimron says, is that why some say the mesh collider is bad since meshes can be convex? Nope, no. Mesh collider is bad because you're colliding with several different, you're creating a mesh collision system, which is way more complex in when it comes to calculations. I have to, kind of do a calculation between one part of the mesh and another. That means there's multiple collision areas, and that's why it's more complex. It's more accurate, right? When we're forming a mesh, but it's super accurate. But on the downside, it's super computationally expensive, and that's why we limit how many of those we use. Shimron, for example, if I want to have to bound a concave area, right, as an example, then I might want to use a mesh collider, right? I might want to try doing that. The problem with it is, again, it's how it does the overlap, okay? All right, so again, representation assumes that the developer uses it correctly, and it does no testing to make sure the polygon is convex and has vertices in a clockwise order. We have to kind of load it up properly. That's what this implementation requires. We're assuming that everything is loaded up properly for this convex polygon, okay? All right, so those are the different kinds of bounding shapes. Let's think about some intersection tests. So when we do intersection tests, we want to talk about some useful tests we want to use. First, this section kind of explores whether an object contains a point. So I looked at an object. Does that point lie inside that object? If it does, intersection, right? And then it looks at intersection between different types of bounding volumes, right? And then finally, it looks at intersection between a line segment and other objects, which is very important. This line segment and other object is like ray casting, rays, right? And finally, the section covers how to handle dynamically moving objects. So if I have two objects that are moving, how do I detect a collision, right? So this is kind of useful for you with assignment, the next assignment 3, part 2. Right, is what we're covering here a little bit. So, okay, contains points tests. So if I want to make a function called contains point, all right, and you can use contains point for all types of different bounding volumes. So testing whether a shape contains a point is completely useful, right? Why? If I want to know if this point, I can choose any arbitrary point in a bounding volume and say, okay, check this vertex. Is this vertex or any other vertex across this line segment, does this line segment fall within this other thing? I can check each point on the line segment, right? I can march across the line segment and I can check if one point is inside of, any one of those points is inside of a bounding volume. And in addition, some shape intersection algorithms rely on finding the closest point, right, to an object, and then figuring out if that point is inside the object. Right, so finding the closest point, we'll kind of realign this for next writing. So the closest point, right? This closest point idea is super important. If we know how to find the closest point to an object, it doesn't matter how an object is oriented, right? If I see there's a vertex, that's the closest point, the closest vertex. As an example to my object, then I can detect if I'm going to have a collision very soon as well. All right, so I can predict what's going to happen. All right, so sphere contains a point. How do I know if a sphere contains a point, right? And to figure it out, first, the distance between the point and the center of the sphere is important. If the distance is less than or equal to the radius, then the sphere contains the point. Pretty simple, because sphere collision detection and intersection tests are the easiest, most straightforward that you can have. That's why you've been given that as assignment 3, part 1, sphere intersection, no problem, right? So because the distance and the radius are both positive values, right, you can optimize this comparison by squaring both sides of the inequality. And this way you avoid the expensive square root, right? Because that's something we've been talking about already. So you want to use squared distance instead of actual distance with square root, okay? So if I say sphere, if I have my sphere struct and I add a contains method to the sphere and I drag in a point, I say, okay, this point here, let's compare if this point is inside the sphere. I can say that let's find the squared distance between the point that I'm adding in and the center of the sphere. Let's get that squared distance, save it here. And then once we have that squared distance, as an example, we want to say that we want to return a Boolean, true or false, if the squared distance is less than the squared radius. If the squared distance is less than the squared radius, the sphere contains that point. Okay, pretty straightforward. By the way, we can do the same tests with two-dimensional points, point and circle tests. Very, very useful, point and circle tests. And how? Well, point and anything. If I have my mouse location, X and Y, as an example, and I want to use I want to kind of hover over, I'm going to make my own buttons, as an example, and I want to hover over that button, and I want to see that my point is contained inside of that that object. I can do this pixel perfect calculation. I can say, is my point inside of that if I just touch that that button or whatever, any kind of shape, whether it's circular or whether it's a rectangular, I can get a result. I can say, yes, it touches, and I can have an event occur. All right, so that's something that is useful for us. We can also do the same idea, point and sphere. If I do a raycast, right, I kind of raycast my object from 2D to 3D. So I kind of cast it along, you know, kind of a normal that goes from my screen. So imagine again, if I have my screen, this is how it works, right? So in 3D, you know, as an example, I might have a screen that's 2D, but I might have a box that's over here in 3D. Sorry, I'm going to draw this poorly, but hey, what the heck, right? So here's my box in 3D. Yay, I'm drawing it terribly, but you get the idea, right? And I want to use my mouse to kind of touch a point in 2D. So I touch it like this, right? So there's my point in 2D, right? And then this point in 2D gets basically sent down that a ray gets cast from here down to the box. And we want to calculate two things. Does the point that's here in the box, when I calculate where that point is, we don't care about, I want to translate, you know, kind of 2D space or screen space to world space. I want to calculate if this point that when I'm raycasting is actually touching this box. And if it is, we've got a collision. We can do that with things like three-dimensional buttons, okay? Or if I want to drag and drop an object in 3D, right, with my mouse, that's another way of doing it. All right, so pretty cool. Right? That's what it does for us. Okay, how about AAVB contains point tests? So given a 2D axis aligned bounding box, again, this is really great. A point is outside the box if any of the following cases are true. A, the point is to the left of the box. The point is to the right of the box. The point is above the box. The point is below the box. If none of these cases are true, then the box must contain the point. Okay, that's the way you check it out, right? And you can check for this by simply comparing the components of the point to the min and maximum points, or we like to call these the extents of the box. For example, a point is to the left of the box if the x component is less than the min.x value, whatever that is. And here is your AAVB contains. You pass in a point. We check to see if you know, the point is outside the box. If it's not, then it's the point it contains that box contains the point. Okay, so point AAVB tests, really, really important, and amazing what you can do with them. Capsule contains points, right? for testing whether the capsule contains a point, you first compute the minimum distance squared between the point and the line segment. Remember, a capsule is just a line segment, and then with two circles or spheres at the end. Okay, that's all it is. So I can sit there and say, okay, well, so let's take the minimum squared distance between the line segment and the point. That's the first thing. And once we know if that's true, we want to compare the minimum squared distance with the radius squared, the radius of the capsule. If the minimum squared distance is, or the squared distance is less than or equal to the squared radius of the capsule, the point is inside the capsule. Pretty straightforward. Again, for capsule type collision detection. All right. Convex polygon contains the point. 2D tests. All right. So now this is a little bit more complex. So there are multiple ways to test whether a 2D polygon contains a point. Again, going back to Shrimron's point, if I use a mesh collider, think about this as a mesh collider in some ways. Why? Because I have a mesh of triangles. That's really what I'm looking at for a polygon, right? Now, again, the assumption is this is a convex polygon, not a concave polygon, right? So one of the simplest approaches is to construct vectors from the point to each pair of adjacent vertices, right? As an example. And then you can use the dot product and arc cosine to find the angle formed by these vectors. So again, A plus B plus C plus D plus E all adds up to 360 degrees, right? Must for that particular thing. If the sum of all these angles is close to 360, then the point is inside the polygon. Otherwise, the point is outside the polygon. All right, so I take this point and I put it outside the polygon, and if it's not close to 360, then it's something else. It's not inside the polygon, right? Because inside the polygon, if you think about this, right, then I could, if I add all these different angles up, right, then it's the angles of a circle, right? These regions of a circle. This is the region of a circle. This is the region of a circle. So is this one, and this one. We can detect if a point is inside of a polygon. All right, and the code for this type test is here. Polygon contains. I'm not going to go through this one. Okay, so that's point and bounding volume. Now we want to do bounding volume tests. Okay, very common to compute intersection between different bounding volumes. For example, imagine that both players and the wall use AAVBs for collision. Okay, when the player tries to move forward, you can test if the player's bounding volume intersects with the wall, and if the intersects and it is happening, then you can fix the player's position so that they can no longer intersect. They can't move, right? They can't move in that direction. And this section doesn't cover all the possible intersections between different types of bounding volumes discussed earlier, but it touches on some important ones. The ones that you most likely will see. This is one that you should be using right now for your assignment 3 part 1, sphere intersection test, right? So how does this work? We have the square distance between the centers, right? And the sum of the radii, we add the sum of the radii up, and we want to see that the square distance is less than or equal to the square of the sum of the radii. Then we have an intersect test. That is the simplest thing you can possibly do. And your calculations that you're using in Unity should be something that looks like this. Yes? That's an intersection test. For any object, any ball that's in Unity with any other ball, you should have this kind of test happening. Am I right? I know, guys, it's not the most important, exciting stuff, but just giving you some hints for for how to do this. All right. AAVB versus AAVB. All right. So this is something that we can see here. So again, the logic for testing AAVB intersection is like the logic for taking AAVB contains a point logic. Same idea, actually. And you test for the cases where the two AAVBs cannot intersect. If none of these tests are true, then the AAVBs must intersect. So it's almost like the other way around, right? For 2D AAVBs, box A and box B do not intersect if A is to the left, right? Or A is to the right, or A is below, or A is above, right? That's the idea behind it, okay? And so too, it's the same with the 3D test, right? So here it is. Let's switch from 2D to 3D. It looks exactly like our 2D calculation that we have in our Collision Manager and SDL Engine, but we just added a third dimension. Exactly the same. Okay. So that is how you kind of think about when we talked about AAVB tests. That's how you think about it. Is my whole shape to the left of, to the right of, below, or above my other shape? If it's true, if any one of these conditions is true, right, then you don't have a collision. Otherwise, if none of those collisions are true, you have a collision. That's the way to do it. Okay, you have an intersection. Okay. So this form of AAVB intersection is an application of the separating axis theorem, which states that if two convex objects A and B do not intersect, then there must exist an axis that separates A from B, which we talked about before. Okay? Sphere versus AAVB test. Sphere versus AAVB test. For the sphere versus AAVB intersection, first you need to calculate the minimum distance squared between the center of the sphere and the box. The algorithm for finding the minimum distance between a point and an AAVB test are each component individually. All right, so that's what we do. And for each component, there are three cases. The point component is less than the minimum. The points component is between minimum and max, or the points component is greater than the maximum. Okay, in the middle case, between min and max, the distance between the point and the box for that axis is 0. In other two cases, the distance between the point and the box for the axis is the distance to the closest edge. Okay? And you can express this with multiple max function calls. For example, the distance in the x direction is as follows. Math max with min x and then minus point x. So the point with the minimum point, the minimum extent, that's what this is, vector, and the point, the x-axis component for the point that you're passing in, and you don't care so much with 0, and you compare this maximum between this and 0, which one is maximum, right? And it will return which one that is. Min minus, if this is a negative value, right, as an example, then it's going to return 0. Okay. And again, the change in x, then, we can say that we're going to take that original value, whatever that is, we just got, the minimum value, and compare that minimum value that we just got, or the maximum value we just got, by comparing the minimum and the point x with the that value and point x minus max, and then we can find what the maximum is between these 2 points. So is it on the right side or on the left side? If not, it's going to be 0. Right? 0 means that it's going to be that other case, the case where it lies between min and max, somewhere in here. Okay, so 2 max tests. And this works between point.x is less than min.x, then min.x minus point.x is the largest of the 3 values, and the delta for the x-axis. Otherwise, it's the other way around, and that's why it's really great. So this is the minimum distance squared between a vector, a point, and an AAVB. So this is the first part of sphere versus AAVB test. We want to know the minimum distance squared between a point, right, and the AAVB. Once we have that, then you can implement sphere versus AAVB intersection, and you find the minimum distance squared between the center, that's the point we care about, and the AAVB, right? And so we say that if I want to do and this is something that you're going to need to do, guys, for maybe assignment 3 part 2, as well as if we're going to have a practical final exam, this will be something that you want to be able to do as well. An intersection test between sphere and AAVB. Okay? So again, very common. We're talking about very basic shapes that you're doing collision detection with. You're making different kinds of colliders here, right? And so again, I have my minimum squared distance of the center. That's the point we care about. And the box, we get that squared distance, and we compare that with the radius of the sphere. And if the minimum squared distance is less than or equal to the radius squared, we know we have an intersection. Okay? Cool. Capsule versus capsule. All right. Now, here's something interesting. We know that capsules are kind of essentially line segments with with a radius. That's what they are, right? line segment with a radius, if you think about what a capsule is, which is very nice. Because both capsules are line segments with radii, you first find the minimal distance squared between these line segments. All right, so we say, okay, distance squared line segment, minimum distance between line segment A and line segment B. What's that minimum distance? And once we do that, we take the squared radii and we compare the squared distance with the squared radii. And again, if it's less than the squared radii, we know the sum of the square radii, we know that there is an overlap. Okay, and those are the basic tests that we can do. Questions around any kind of basic intersection. So we've covered AAVB, AAVB. We've covered sphere AAVB, and we've covered capsule, capsule. Okay, there's other ones you can cover. Example, capsule, sphere. You can do that. You can cover capsule AAVB, right? You can also, there's other ones that aren't involved here as well that you can do as, as well. Like, for example, plane sphere, which is something that you're talking about now with Joss, right? So think about this. If I was going to design something in Unity, right? And what if instead of using planes, which is might be, again, a challenging calculation. Let's just kill this thing so it doesn't kill my memory. Right? And I'm not saying that this is a fix by any means, but wouldn't it be easier to do a capsule AAVB test? Oh, sorry, a sphere AAVB test. And if we assume that all the planes are actually boxes, just saying, right? So this, by the way, does not tell you, here's something that none of these things tell you. We're going to talk about that in collision response. How far they've penetrated. We don't know how far they've penetrated, and where to put them back. We have to reposition. Whenever one of the proper collision detection is not just about detecting the collision, but repositioning is the next phase, right? So I need to always reposition an object so that it's not touching, as an example, the other object or just touching the other object. Okay, that's what we want to do. Okay, so keep that in mind when we're doing that. The other thing that we run into when it comes to making a good collision management system, right? I want to make a good collision management system, right? So let's draw that out again. So imagine if I have a screen, and here's my screen space, and I have let's suppose these are boxes. They're not 2D, they're 3D objects, right? So I have an object here, and we talked about this briefly, another object over here, right? Some kind of spherical object here. I have an object here, and I even have some kind of weird, convex, polygon. It's almost a convex polygon, right? A convex polygon that you want to check to see if you've got collision detection with, right? So if this is my principal, if this is my player, right? And we've talked about this before, then well, I've got to kind of start checking. I got to say that I want to do, and let's suppose this is a crate here, and this is another crate. Okay. And this is some kind of weird rock, okay, that's happening. It's falling on the player's head, but it hasn't fallen on the player's head. So this is a rock of some kind of irregularly shaped rock. Maybe it's irregular. And we've used a polygon collider system. We've made our own polygon collider system to do this, right? Again, the question always for you should be, should I? Should I do it? It's perfect as an example, but should I? And the answer probably should be, no, you shouldn't. Not unless you really, really have to, right? The other option is to break down an irregular object with one or more of these basic shapes, okay? It's still less computationally expensive a lot than trying to make it perfect, okay? Especially when you're doing it by hand. But anyways, what I'm talking about is when I start doing collision detection, now I'm starting to think about how I'm going to do it. And what you might be doing is I want to create, kind of a container, right? I want to create a container that contains all of these collision shapes, right? the crates and the rock or whatever else you have in there, right? And I want to start checking between the player and the crate, the player and this crate, the player and the rock. And that's okay, right? And how about, I also want to check between this crate and that crate, and this crate and the rock, and this crate and this rock. Okay, those are all the things I want to start checking in a physics system. Okay, so look at all those checks. I'm doing that every frame. Could there be a better way of constructing this scenario, right? What do you think? We talked about a couple of things that we can use, right? So what did Joss give you? Did Joss give you any container or anything like that for this idea? And let's just for our purposes, let's not have an irregular shape, okay? Because we don't want to complicate things. We'll say there's no irregular shape. The rock is actually just another sphere, okay? So we'll say a rock, it's not irregular. We surround it with some kind of spherical bounding box, right? Because it's probably close to this, probably close to this. There we go, there's a rock. And so we want to start comparing these shapes, but remember, we want all of these shapes to collide with one another, right? So is there a better way than doing player, crate, player, rock, crate, rock, every single frame? And what if there were 3,000 objects, 2,000 objects, 1,000 objects? You know, how would that work? Is there a better way of doing it? What are your thoughts? We've kind of talked about that. Sophia says a grid. Yeah, we could. So we could split this off and we can make a grid. But how do you define that? How would you code that up, Sophia, in Unity, right? So here's a grid. I could kind of split this off inside of this. So I could create a grid and I can say, okay, cool. But you'll have a condition where it's moving. You're not going to snap the grid when you move, right? You're not going to snap the grid. You're going to start subdividing. You're going to subdividing, the surface, kind of the world into smaller areas, right? Again, I'm just like drawing these with my terrible drawing capabilities right now, just, freehand here. And so they're not going to look even. I'm so sorry. Okay, but the idea is the same. So I've kind of split this off and let's just roughly do the same thing here. Okay, so we're going to make this grid. And we're not using anything, just drawing really quickly so we can have this stuff happen. Okay, so here's a grid. And I can make the grid more granular, right? Samuel says, if I stress test and I put a lot of spheres in the scene, some of them don't update properly. Absolutely, you miss some because there's just too many calculations at once, right? So let's talk about this. All right, so think about if I break this thing down into a grid, there's overhead for the grid too, right? Because we're making a grid and we're saying we're going to try and compare, a way of doing this with trees. Okay, so I want to talk about collisions with sparse octal voxel octrees. You're gonna like this one. So if you look that up, all right, so let's just look that up in terms of the way it's going to work. So if I say sparse octal octree, sparse voxel octrees, as an example, right? So let's take a look at those, right, and what they look like. This is a sparse voxel octree, right, idea, where what you do is you have a shape that looks like this, and you start at one particular location. So this is the top part of the tree, which is the outer, kind of we're talking about what we normally talk about, which is, you can also look at it like this. Here's another variant of this. We have an object in different parts of the screen, and what we want to do is start at the very base part up here. Is it in here? Yes. Okay, cool. It's in this part. Now we go to different quadrants. We split the area down into quadrants, right? And we sit there and say, okay, is it in this quadrant? No. Is it in this quadrant? Yes. Cool. Okay. Is it in this quadrant of that quadrant? Kind of thing. Yes. Okay, cool. Split it up again. And we keep splitting it and splitting it and splitting it until we can detect exactly where an object is based on this stuff. Where is it? Kind of thing. And you can find the exact grid location depending on how kind of how you detect and what does your, your grid look like, you can use, kind of slices, grid slices, depending on how thick. This is only in 2D, but let me just go back to my little drawing here. So we keep on slicing it. So we sliced it this way, and now we slice it this way, right? So we kind of create this grid, and we can feed the grid into a tree, right? We can feed the grid into a tree when we need to. All right, so again, I'm going to break this down. And again, this is quite still, it's not granular enough when you do it this way, because you can see that all the objects that are inside of my scene still aren't within a particular grid, right? But they overlap, right? So we can say that, well, if we do an intersect test, we can say that, okay, this crate, it actually is in grid locations, let's say, for example, 1, 2, 3, 4. It's not true, but let's say what they are. And this is in grid locations 4, 5, 6, 7. This one's in 8, 9. This one is in 10, 11, 12, 13. Well, guess what? None of these things are the same, so there's no chance for intersection. Right? Sparse, voxel, octree. Yeah, you like that? That's a good one. Neil says, should we use trees for assignment 4? No, you don't have to. Sharon says, what about checking collisions for objects in the camera, in the view of the camera, you mean? Yeah, you could, but that only means that you're only looking for things that you can see. Who cares about the other objects when they're outside the camera? That just is an optimization step. So this is definitely a way of optimizing, because what you can do is you can say, okay, these are all the objects, and if there's a grid, what are you doing? You're doing collision tests, if you will, or detection tests. Is the point in any of these points here, take the extents, and is a point, any of these extents, inside of one of the grid spaces? If the extent, which is a point contains, we can do point contain tests for this thing, then we can start marking down how this works. Neil said, with Joss, we use this. Should we switch to square magnitude? Sphere collision, custom physics collider sphere, A, custom physics collider sphere B, vector 3 displacement, position minus position, distance, magnitude, minimum distance, radius, plus radius B. No, I think this is pretty good what he's got. It's okay. I mean, it's, again, we're talking about, you could definitely use another calculation if you want to do sphere collision detection. The thing I showed you is going to tell you if you're colliding. That just returns if I'm colliding, right? And what does this return? Because it says sphere collision, it returns void, I'm guessing. It just checks to see if it's colliding or not, right? Custom physics collider, sphere collision. Yeah, so I mean, it's really up to you. You don't have to use this. What Joss is basically showing you is his way. He's building it up, right? Well, that's the thing. The response is the big one. So this what I'm talking about just does detection. It doesn't do response, right? But what I'm trying to figure out for you guys is, and remember, you can split up detection and response. What I'm trying to figure out for you guys when you look at all these things is you got to think about it and say, do I want to do every single one of these? Whereas even if I put it inside of some kind of array, right? This whole thing is in a 3D array, as an example, and within a specific bounding area, I can sit there and say, okay, cool. How many of these things I go through? I can just basically say no, 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 yes, yes, no, 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 yes, no, no, yes, yes, no, yes, 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 no, no. And that's what I can do with each of these things. This object contains something, right? That's what it means, right? Okay, how about this? Does this object contain two somethings, right? If this grid contains two somethings, right? So something that looks like this. Here's another crate, right? And I'm just drawing this. So I want to just trying to, work it out with you. Let's think about this for a second, right? If I have two objects that are in two different areas. And in this particular case here, we have a situation where, we have a situation where we can, kind of, let's just do this. And let's just draw an object here for you guys. So in this situation here, we have a box, an area where we potentially have a collision. That's the only area where I have two things. There's two objects. There's 2 points from two different objects inside this area, right? And we talked about this, a concept, right? This concept that we talked about before. What do we call? What was this called? This thing that we're doing, right? Is a basic concept. Does anyone remember? Let's see if you guys do. It's called broad phase and narrow phase collision detection. So broad phase and then narrow phase collision detection, right? Broad phase, narrow phase, this idea of broad phase, narrow phase, whether you use sparse voxel octrees or some other kind of grid-based collision detection, right, is the ability for us to sit there and say, when do I start checking? Do I check here? No, nope, nope, right? I wouldn't check this object with anything else. I'm not even going to do collision detection with this object, or this object. The only one I really care about is between these two, right? Because that's the only case where there's a box contains 2 points from two different objects. That's when I start checking. What are the objects? Those are the ones I'm going to check, right? So it reduces the chance of you having, a complex system, right? What other things can you do, right? Well, another way to do this, okay, so fine, I can make use of a sparse voxel octree by basically loading this into different regions. That's another thing I can do. This is kind of a grid base. Sparse voxel octrees use a different method that it showed, right? And there's actually, the method is well known. It's not like I would be making it up or whatever, right? So you start off and you start partitioning the screen. So you say, this is the first partition. Does it exist here? Does it exist here? Does it exist here, here, here? Well, I have an object, that's here and here. There's an object, but I'm looking for, objects that are in the scene, as an example, and I want to start partitioning. So I say, okay, well, let's suppose I want to find this object. Then we partition again, right? That's the second partition. We look at, that's the tree. The first tree is this one. Does the object we're looking for exist in this root? Yes. Okay. The second part of the root, we're going to do a clockwise ordering, where this is the first child, second child, third child, first, second, third, fourth in a clockwise ordering, right? And I go here and I go, okay, so it's not in, is it here? Yes. Cool. Stop. Go into this one. And we have objects in here. Cool. Now, let us do, this is the root. So it's a recursive algorithm. And let's look at this thing. Do we have objects in here? Do we have objects in here? In this quadrant? Do we have objects in here? Right? And do we have objects over here? We have objects in here. Cool. Okay, let's make this the root. Do we have objects in here? No. Do we have objects in here? No. Do we have objects in here? Yes. And we also have an object over here. This part here is yes, right? As we're kind of zeroing in on this object, let's undo that and actually draw it properly, or as best as we can, right? Cool. Those are the two that count. These two are omitted. So now we're going to go to the first one, which is this one. Okay, cool. Do we have objects here? Yes. Then we can split this off into its quadrants. Do we have an object here? Yes. Cool. Let's split this off. Do we have an object here? No. Do we have an object here? No. Do we have an object here? Yes. Right? And so we would split this off over here, and we can find, look at this, the extent of the object, right? So that's the way it kind of detects this. Neil says the process of inventing all this must have been so interesting. Well, it's a way of mapping three-dimensional objects and having details about them, kind of when it comes to objects that exist. And you can say that, well, if two objects, you can say two different objects contain. So this is kind of the way sparse voxel octrees work. But the idea is that you're going to use this idea of broad phase and narrow phase collision detection. Another way that I've heard it done is where you have slices. So you have very thin slices of the world, right? So you kind of make a grid with these very, very fine slices, right? And this is another way of doing it. So you create all these slices, and this, let's suppose this is the z-axis, right? So this is going up, or in the case of Unity, the y-axis. And what you do is you create these planes or these bounding areas this way, right? And these bounding areas are just boxes, AAVBs, right? And you say, okay, cool. Are there multiple objects? Is there more than one thing with this AAVB? No, 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 no. So there's a bunch of AAVB collisions, right? And if it is, if you have, let's say, if you did that with this one, and you can say, well, there's no here, no, 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 there's no one, but here there is, right? If I do slices, right? So here's slices that we're talking about. We slice this way instead, right? So here in this slice, we have two objects that inhabit this slice, two objects. Okay, do collision detection. Right? That's another way of doing it. And again, it's optimizing these things, these processes that we're trying to figure out. Okay, last thing. What about when it comes to, and I'm just going to kind of do a new one. What about when it comes to data structures, right? When it comes to data structures, how do we align the collision shapes? So we have an array of collision shapes. So some kind of, I'm just going to put it like this. I like pseudocode, a array of collision shape type. Okay, that's what it is. You can have an array. It could be a list. It could be some kind of collection of collision shape type. Okay. And we load them up inside of this container. So the collision shape can be different ones. I can have a collision shape that is a cube. I can have a collision shape that is a sphere, right? I can have a collision shape that is a polygon, right? It doesn't matter, right? I can have multiple collision shapes of different kinds in here. And if I create an array or some kind of collection of collision shapes, then all I want to do is, it's just linear. I just kind of go, I take this one, I go this one, 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 and do it that way, right? But first I create an array of collision shapes, right? And you could easily make this is a linear sort, kind of, that's what you're doing. You're checking to see every single object with every other object, right? And this can take, in the worst case, it, from a big O notation perspective, it's very poor because you're going linear, right? I could do that. And I can do it other ways as well, right? Where we can sort the shape based on its location, right? So one of the things that we have is we have kind of the center of location, right? We have almost like the center of mass that we talked about before, right? So this is something that I've seen also. So center, let's say the object center, okay? So if you could find the object center, it's easy to do for spheres. We know what that is. But what about the object center for this, right? How would you find the object center for a cube or a rectangular prism of some kind? How would you find that? So what you do is you say, okay, is the object center, if I take this thing and I take this thing and I say, are these close enough, right? As an example, are these within a certain, the radius of the sphere? Is this within the radius of kind of the extents of the cube? And I can check each one of them this way. But what if I split it up and I ordered this in terms of the distance from the origin, right? So if I have, again, a map that looks like this, let's say a map, so this is my screen, and let's suppose the origin in Unity is here. Again, I'm giving you ideas here. Hopefully this will help you, not hurt you. Let's suppose this is the origin in Unity, and I sort them according to the distance from the origin, some origin point, right? Where I have, maybe I sort it by negative values and positive values, right? It really depends on how you want to do this, but typically we do it in a kind of a sorting order that goes like this. So negative, negative to positive, positive, or sorry, negative positive to positive positive to something like that. You order your map in some way, okay? Obviously, the easiest thing would be if the origin was down here. So if this was the origin, okay? If this was the origin, then it'd be simple calculation, right? To kind of say, I want to sort these things according to the distance from the origin. Farther away from the origin, that's how it's going to be, right? So this is the origin. The farther they are away, I want to have items closer to the origin and items farther to the origin sorted inside of this collection, right? By the way, it doesn't matter where you put them, right? Whether you put the origin here or whether you put the origin here, if you sort it based on distance, let's put some shapes. So here's one shape, and let's put another shape over here, right? And let's put another shape over here, right? Then when we load this collision shape area, we load it according to distance from the origin. We have some origin, we load them according to distance. If the distance from the origin on these shapes, so the distance from here to here, from here to here, and from here to here, that's how we're loading them into this collision array, if you will, or something like that, right? We start off with this one. Okay, cool, this one. Is there anything else that's close to this one? So if we were to split this, if it's sorted, right? And if I say that if I take this and I split it in half and I go here, is this shape, whatever it is, you know that this is the smallest shape. How about the one that's here next to it? Is it close enough to this shape? Is the distance between this shape and this shape from the origin, are they close? Are they close in number, right? There's some offset. If so, check collisions. If not, if they're very, very far away from the origin, like this one is like, let's say 10 units from the origin. Let's look at this, right? 10 units from the origin. There's some issues here, okay? I'm not going to suggest this is the only way, but this is 10 units from the origin. This is a distance. And this one here is also 10 units from the origin. I've drawn it differently, but let's suppose it is, right? Let's suppose these two are 10 units from the origin. And this one is 50 units from the origin, right? And if we've put everything in kind of a distance order, right? Then maybe checking these two things is okay, but not checking this one. That kind of stuff, right? That's another way of doing it, where you sit there, oh, what's the distance from the origin? Well, are these close? Kind of thing. And you can do better, right? You can say that you can split this off into quadrants, just like we've done before. And we can say that if the origin is right here, we can say that any quadrant, this is similar to the sparse voxel octree idea, right? But it's maybe a simpler way of doing it, where we say that, let me just undo. We say that we break it down into these regions. This is what you want to do, where you say that, what about if I was to start looking here? Okay, so anything that's in the positive area, right? If this area here, it's positive, all positive values. So because the origin is 0, 0, this is positive x, positive y, positive z, right? Positive, 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 right? In this quadrant up here, right? If an object that I've loaded into the collision array, right, is close, right, within, let's say, X number of units to the origin, check. Example would be if I have another object in the same area, right? They're not the same. If they're the same or close, and when I say close as in maybe some value, you could make it the extents. You have what's the extent, the distance from the object's origin, right? You can kind of calculate almost like a radius around any object, right? From the center to its extents, right? If another shape is within, from a distance from the origin, is close to this, that's when I check, right? And I don't check otherwise, right? So again, you might say to yourself, well, what does this save me, right? Because if it's not saving me anything, then who cares? It should be your answer, right? It shouldn't be something that is just some fancy algorithm. You want to make sure that you don't check these ones, but you do check these ones, the ones that are close. So let's say, for example, I put another object and it's fairly close, like it's here, right? But it's not quite as close as this one. So maybe this is like, I don't know, something like 12 or 13, right? So we're going to draw a line from here to there, to that center. That's when you check. You start checking when it's close enough, right? As opposed to something that's way wacky outside of that point, like something that is way over here, right? Kind of thing. So something that's way farther than the origin, like over here, right? There's a thing for this as well. There's a name for this. I forget what it is. But, let's say, for example, this is like 35, right? You don't want to check this one because this is 35 away from the origin. It's way down here, right? It's way down on the list of the on the array. You just want to start checking these ones, the ones that are close. Check the neighbors, right? If this one and this one and this one and this one, you check certain a list, to a point where it's greater than that, then you stop checking, go to the next one. Stop checking, go to the next one. Stop checking, go to the next one. Keep doing that over and over and for each quadrant. You do it for this quadrant, then you do it for this quadrant, then you do it for this quadrant, then you do it for this quadrant. And you have your array can be sorted in different quadrants where you don't check, or you can have 4 different arrays if you really want to. Okay. Why? Because at the end of the day, you want to reduce calculations. Thousands of objects here can make it so that it's not as bad. Okay. Would checking the distance between the objects be too much of a prerequisite? No. You can make it so it's squared distance, so it's the calculation doesn't use square root or power. You don't want to use that for sure. You're doing a square distance. You're going to quick distance check between everything to everything is what you're saying. Yeah, it is okay for now. But what if I have, instead of the amount of balls that we have in our example, we have 1,000 balls? Would it be good then? That's what I'm getting you guys to think about, because your physics engine, right? Even Unity struggles when you have thousands of objects, right? And it uses more advanced collision detection algorithms in order for you to do that, right? And it slows down because you're doing, 100 balls with themselves, right? So you're doing a calculation from each ball to each other ball. Every ball has a chance to check with 99 other balls, as an example, every single ball, right? So it's like a, factorial, right? And that's pretty crazy, right? 99 factorial. So it's insane in terms of how many calculations you do. If once you go beyond 100, let's say you do 1,000, oh my God, you're never going to do a great collision detection. And we use this system that collide with one object with every other object. We did this in in 2D calculations in our SDL engine, right? Because we have a very little collision manager, and it just collects checks collision shapes. That's all it does. What I'm saying is, can we organize ourselves? Can we optimize by organizing ourselves in some way, right? By doing this idea, again, going back to this idea of, broad phase and narrow phase collision. That's the idea behind it. Don't check unless you have to, right? That's the idea. Yeah, so something like this is the way you want to go, okay? So when they move, you update the array. You sort the array. If this is an object and it moves and it's farther away from the origin, you update the array. Once it moves, you update the array. You sort you put that object in the right sorting order. Again, there's an overhead to this, right? I'm not saying there's not an overhead, but is the overhead, the calculation overhead for creating this, this collection of collision shapes, is the overhead greater than the calculation, the computation condition that you've created, where I'm calculating objects with every other object? That's the thing you have to consider, right? And if the answer is no, right, then kind of figure out some kind of optimization. So Samuel says, for this check of displacement from origin, would the object update its own displacement from origin point while moving? Yep, you can do that, but you can do that anyway. You can just say the magnitude. What's the magnitude from the origin? And now magnitude is distance. So you'd want to use squared magnitude. Yes, that's the idea here. We want to try and get it to, O to the n instead of O to the n squared, for sure, because it's crazy, right? We want to try and reduce the complexity of the calculations. We want to have less. We want to do less calculations and filter through this somehow. And a good thing to do is, you want to look at some articles about collision optimization. Collision optimization, right? In 3D, right? So that's what you want to kind of look at. And collision detection is one thing, but collision optimization is how do you do optimized collisions, as an example. And there's some great articles, and we'll talk about collision optimization later, where it talks about how to do that. And there's some articles, answers, and one of them, look, query only nearby objects. That's 3 of the answers that came up. On a grid, on a tree. Those are the 3 options that they talk about it, right? Discard checks instead of collision, right? Discarding checks instead of collision. There we go. And query objects by their kind, right? And so on. So there's lots of different ways of doing it. And I'm sure if you looked it up, you would see other kinds of formulations that, that give us some solutions. What I'm going to do for you guys is I'm going to see if I can come up with some optimizations for the final day. One of the things we talked about here is particle systems, right? So we said we're going to be working on particle systems. How do I do a particle system in Unity from scratch? So I'm not using Unity's particle system. I'm making my own. How do I do that, right? And when I create particles, what are particles anyway? Should I use them as objects, game objects, right? Or not, right? So how do I put that together? Shikang says, do we need those for our assignment? No. Miguel says, we are learning how to work with trees. Awesome. So then think about trees. Think about tree detection, where I kind of look at the tree. The first part of the tree is the large, that's the broad face. The top of the root is the broad face. And then I check different quadrants. The tree would have basically, it wouldn't be binary trees. You could make it binary, right? But really what you're thinking about is, okay, here's the tree, and the tree is going to have 4 roots, right? Equivalent. Just like we saw in the diagram, right? For sparse voxel oct trees. Take a look. Each root has 4 leaves, right? Each root has 4 leaves. Each root has 4 leaves. So that's what that's what it looks like. And so you can start thinking about where these objects are and if they're colliding. As you get closer and closer in here, what you're starting to do is map objects in a smaller grid, right? Where you have much more, kind of granularity, right? What we use, trees are typically used in a recursive algorithm, all right? A recursive algorithm, okay? Okay, and again, take a look at sparse voxel oct trees. They're awesome. There could be some, algorithms you can find online to help you out. And they're totally valid as long as you reference them, from an optimization perspective only, right? You can start thinking about them. Maybe you can make something of your own. Okay, questions around 3D collision detection. We've talked about different collision shapes, maybe some of them that Joss hasn't talked about yet, but he will coming forward in his next set of labs. He's going to start talking about AAVB type collision detection and other types. Okay. Any questions before we go for the day? All right. Last thing is assignment 4, which is assignment 3, part 2. That's what it's going to be called this semester. Assignment 3, part 2 is going to be released and updated by Friday. That's tomorrow. So hopefully you'll have a chance to take a look at that. If we can if I have time, I'll record a small video around what's required for assignment 3, part 2. Typically, it's going to be an extension of assignment 3, part 1, which allows you to do more extensive collision response, bouncing balls, okay? Yeah, we're going to talk about tunneling and how to deal with that next week, right? Because tunneling we can use something called swept spheres in order for us to prevent tunneling. But typically the way we want to do it, Samuel, is if we have an object that's moving, that's small and fast, we want to slow that object down and we want to make it bigger, typically. That's what you want to do. That's the way you do it. If it's a small, fast-moving object, typically it can tunnel through anything. Unity has a way of turning on different types of collision detection, but because you're making your own, you have to think about how that collision detection works. Okay, how are you going to have more slices of time? Well, I can speed up the number of calculations, so I can increase my frame rate, right, as an example, or I can slow down my object. If you turn up the gravity scale, sometimes you get tunneling. You do that because it's going very, very fast, right? So what you want to start thinking about is, can I do a look ahead? Can I do a prediction? Am I probably going to collide, is what you want to say, right? And the way to do that is to use something called swept spheres. So imagine if I have a swept object. Swept spheres kind of look like this. We have a sphere here, and then you have a line segment similar to the idea of a capsule, right? And then you have the sphere at the other side. Did I do it right? No, it's the other way around. It's here, right? So this is a swept sphere. So what you're doing is you're saying that anytime that it goes from the extents from here to here and from here to here, I want to have, if this is a bullet, I want to create almost like a little capsule, a line segment that kind of projects outside of the sphere itself that goes down. And I'm going to say that whenever I'm moving, this is the actual object, right? And so this part is the actual part, let's say. And let's say if I'm moving down, then this part would be the predicted area, right, where I'm going to go. Okay. And if an object lies between, like for example, something that looks like this, we're not quite there yet. We have an object that lies between. Chances are you're going to collide. Okay. Future collision check. Yeah. Okay. So any other questions before we go? Guys, thank you so much. Good luck on your assignment 3. Again, I've extended it to Sunday, this Sunday. That's the best I can do. Good luck, and hopefully you guys have a great experience doing this stuff. All right, take care. Thank you.